Hopefully this won't beep. That was you, right? That was not. Just making sure. I moved a couple of things around, and I did it on purpose because if you notice down here, everybody's paranoid. Again, let's talk about this quickly. What is due on Monday?
Super basics.
Super basics, right? So it can be buggy. It cannot work. I understand that. Don't freak out on me there. It's not like it has to be this beautiful polished thing. And again, what's the intent? Why am I making you go through this? Yeah, because people procrastinate. I want to make sure that you have the basic mechanics in place and that you can start to play with it, because if the basic mechanics aren't any fun, what does that mean you're going to end up with? A not fun game, right? So this is the time that you need to start playing around with this and try to tweak whatever it is that your game is going to be about. It could be about throwing trucks. I don't care. It doesn't really matter. But you need to get a truck being thrown across the screen and see if it's fun or not. Okay, that's the idea behind this. Also notice that I moved some things around. I kind of pushed this gamification down here a little bit later. Do you know why? Well, it's tied with chapter 2.1. Does anybody have the book? Probably not. You're still carrying it with you? You look a little bit thinner than the last time I saw. It's like, that's going to be great in the winter. You're just going to break a sweat when you're walking through. 2.1 is 78 pages, something like that. I am not expecting you to digest all of that material. We'll still talk about it, but I think what I'm going to do is to throw it out there in terms of questions. So if you're going to do anything, go through there and kind of outline what the main ideas of that chapter are, because that's a really long chapter. That's almost a book by itself, and it's just the generic game design. So don't beat yourself up on that. Am I expecting you to still read it? Yeah, skim through it and say, okay, I get the main ideas and things like that, because they are relatively important. Okay, today we're going to talk about audio, unless there are any other questions. Yeah?
Do you ever do audio in Java? Do you ever do audio in Java?
Let's see if I can move this out of the
It's
way.
really difficult in XNA. Really, XNA just makes everything like a lot easier than it should be.
Yeah, no,
Come on. Full
familiar with all the methods that you can pull out of the air without.
And just to make sure everybody saw the email I sent out, I am looking for people who have HTML5. A couple of you have had HTML5 experience. When I say this is a high-profile client, I'm not talking about EA. This is not like Nintendo or something like that. It's a local client, but it's a fairly big-time name. So I can't give you the details until a little bit later. Thanks to those of you who have replied. It is paid, from what I understand. Okay. So let's get into this then. What do you know about computer audio? What do you know about sound?
Vibrations.
Made by vibrations. It's kind of disgusting when you think about it. And here's why. Think about it. I'm basically a piece of meat, and I resonate. And as I blow air through my lungs through this thing, this piece of meat, it vibrates air. As if that's not disturbing enough. Those vibrations hit you, and they hit your ears, and they make you vibrate too. It's kind of gross when you think about it, right? Yeah, but it all has to do with vibrations, right? So that's the fundamental kind of thing that we're going to be working with in terms of just sound. So it's compression of air or some other media. There's some really interesting kinds of things. I don't know if you ever did this as a kid. Did you ever go into a pool with a watch on that would beep?
Yes.
How many people did that? Okay, a couple of people are guilty of that. What's so cool about that experience?
Makes it sound.
You can hear it from forever away, right? Because water is so dense and everything. You could be on the other side of the pool and that a little alarm could be going off and you could hear it, right? So I threw down some strange facts down here, and I'm just being cut off a little bit. But air travels at different rates through different kinds of media. So it goes through air at 340 meters per second. You ever seen a framing crew? They're hitting these things like a house really far away. They hit a nail and you see, and it's just taking that amount of time. Well, if the world was made of gold, if you were breathing gold and this was the medium that we work through, 3,240 meters per second. So the denser this is, the faster it goes through there. Everybody's heard whales sing, these kinds of things, right? That's why it works. Okay. Sounds are made up of high-frequency and low-frequency sounds, okay? By this, I'm not talking about volume. This is the number one thing that people get confused. They think that frequency and volume are the same thing. What's the difference?
Frequency is the length between wavelengths. It's like shorter wavelengths.
How fast the vibrations occur.
Right.
Yeah, right? So yeah, a higher pitch means what? It's faster, right. So we measure these things in hertz and all that kind of stuff. I don't know if these are going to play, but let's try it. Oh, it did. Okay. That's a very low A. Let me play it again.
Whoa. Do you have perfect pitch yet?
I'm getting excited for
Yeah.
number 5.
No, okay. Who just sang "Thus Spake Zarathustra"? Was that you? +1 for you. All right. And then, okay. So these are increasing. It's actually doubling the frequency there. That gives us something called an octave, right? So all of these things are basically the same note, but they have a different octave that they're in. It's a higher pitch. Okay. So make sure that you have your terminology correct. Realize that we measure volume in dB, right? Notice the D is small and the B is capitalized. Does anybody know why? It doesn't matter. Don't worry about it. Okay? We measure frequency in hertz, and notice that the H is capital and the Z is lowercase. Okay? Does anybody know why? No, I don't care. Don't care. And then also, this is an interesting fact, and you will appreciate this as you get older. Humans only hear from 20 hertz, which is really low, up to 20,000 hertz, which is really high. Now, you guys are all probably in your late teens, early 20s, something like that. You have mosquito ringtones on all these kinds of things. I just got to the point that I can't hear those anymore.
Yeah.
I'm 42 years old, and I can no longer hear these things. And I actually got the mosquito ringtone, and I stuck it directly against my ear to say, I want to hear it one last time. And I did it, and I kid you not, like 3 days later, I couldn't hear it. So that's it. And it's going to happen to you. I used to walk into like Sears and all these kind of places that would have all these TVs that were the CRT, the old ones, and they would just drive me crazy. It would be like almost like a dog signal kind of thing just going off. It was really awful. Yeah.
Yeah, I've actually I always noticed that. We had like an old TV in our basement. Every time you turn it on,
You turn it on and you hear that real high pitch.
you realize
When you hit about 40, you don't have to worry about that anymore. Yeah. But anyway, it's kind of interesting. We're going to get into a little bit of the human side of this because there are things about sound that are they directly related to games? No, maybe not. But there's some interesting things that you still need to know. Okay? We talk about spatiality of sound. Spatiality is not a word that you would really find in Wikipedia. But we talk about spatial sense or spatial presence of a sound. And so we have one channel. We call this thing mono, right? Monophonic. In fact, you probably heard this. I've seen a monophonic system that had 2 speakers. How is that possible? It plays the same thing. Understand that there's one signal that is then split out to 2 different speakers. There's a lot of systems that are set up this way, right? So if you have somebody who has a microphone, something like that, and they're walking around, you probably have a monophonic system, right? There's no stereo that's going on. When we have 2 channels, we call this thing stereophonic, okay? What's the difference here? Yeah, independent channels, right? So if you have a FM radio or something like that in your car, chances are you have something like this, okay? The nice thing about this is that we can fade between left and right. We can provide different information per channel, okay? We also have 5.1. Actually, we have more than 5.1 now. But what is 5.1 audio?
5 and the 1 subwoofer.
front, side, back, side.
What is the 0.1? Like, why didn't they just say 6?
There's a subwoofer.
The 0.1 is the subwoofer. Now, there's an interesting thing. If you're really into audio, this is what I did my master's thesis, if you want to think of it that way, at Georgia Tech. I worked in an audio lab, okay, and so I built like self-harmonizing karaoke machines and did a lot of just weird kind of bizarre stuff. We had a giant, when I say giant, we had a giant box that was our subwoofer. It doesn't matter where you position a subwoofer. Everybody hear me when I said it. It doesn't matter where you put that thing. Everybody's like, oh, we're going to optimize it. We're going to stick it. No, it doesn't really matter. Do you know why? How big is the wavelength that this subwoofer pushes out?
The biggest.
It's huge, right? So it's this massive kind of thing, and it's me moving over this way is not going to change the relationship of me to that speaker. Believe it or not, when you get to that low frequencies and stuff, you have a really difficult time telling where it's coming from. You ever been downtown? And you hear it. I had the ultimate experience. I was downtown one time. I can't even remember what city I was in, but I heard bass coming through, and I'm like, good grief, I've been hearing this bass for a while. And it kept getting louder. Just kept getting louder, and I'm like, where the heck is this thing coming from? It was reflecting off the buildings and everything else. I kid you not, like 15 minutes, it kept getting louder and louder and louder till finally it passed me, and it was like shaking my whole body. Okay? Have you ever heard of the Brown frequency?
Yeah.
Now, that's not what this guy was blurring out, fortunately. But believe it or not, your colon resonates at 8 hertz.
What? How many?
That 8 hertz, 8 times per second, right? So if you had a speaker that's going back and forth 8 times per second, that's what your colon resonates. Now, why is this important to this class? It's not. But somebody in France tried to rob a bank using that technology. They walked in, I kid you not, tried to blast the bank with 8 hertz so that people would have to go to the bathroom, and then tried to rob it. And I think they got away with it. So.
Whoa.
But anyway, yeah, so the point one, going back to this lecture, maybe we should edit that part out. What are you learning about, Brown? But anyway, yeah, the point one is the subwoofer, right? And then we get into 3D sound. And this is where it does get a little bit more interesting for us, okay? How does 3D sound work?
It just does.
Has anybody heard 3D sound on a computer? So look, it's not so bad. Most people have, speakers. They have a couple of speakers on their laptop or their PC, something like that. I want you to close your eyes, and this is a stupid kind of exercise. But everybody close your eyes. And what I'm going to do is I'm going to walk over here, and I'm talking, and I'm snapping, and then which way am I going? Over to the other side of the room. Now, open your eyes, and I'm back over here. How did you know where I was? In fact, if I were to ask you just to close your eyes and point to where I'm speaking, you would be within about 5 degrees of where I actually am. How do you know that?
The difference in time when you're here.
Really interesting stuff. Let's talk about our ears. Right? Please do not memorize this chart. Jeff's going to ask extra credit. He's going to ask us to label. No, I don't care about this. You've got an ear canal and you have some stuff. But the real question is, what do these things do? We've got this big wedge of cartilage that's sticking off of our head. Why? It's not just to capture the sound. I could chop my ears off and I could still hear.
It helps you determine direction and stuff.
Believe it or not, so the left-right thing, somebody hit on it, right? If I'm standing over on this side and I'm snapping my fingers, and assuming that you're still facing here, it's hitting your left ear before it's hitting your right ear, right? The time of flight, the time that I'm snapping them, by the time that it hits your left ear, is a fraction of a second off, okay? That's great and all, but now everybody kind of do this. Snap above your head. I know it sounds, you're like, what is this, romper room? No, there's a reason. How did you know that the snap was above your head?
Because I made it.
Because I raised my hand.
Yeah, because you were doing it. I'm serious. Now, knowing that, if I were to snap above your head, you would get the same effect. You would know that something was up there. How? It's hitting both at the same time.
But it's hitting a certain part of it.
Listen, that's what these things do, okay? These things help us when it's back behind us and it's in front of us. You think about it. You're going to all go home, and I know you're going to start doing that. But you have to appreciate it. That's what these things do. Now, do all of our ears look the same? No. And this is the problem that computer scientists have with creating 3D sound. Because what a 3D sound sounds like to me doesn't sound like to you. Right? So to have 2 speakers, we could have it configured where it is perfectly configured for me. But when you sit down, because you have a different shaped ear, it's going to be different. Okay? So that's the tie-in with what it is that we do. So this is another interesting kind of thing that you probably should be aware of. This is called the equal loudness contour. And this is the amount of power that it takes to create a sound and make it appear consistently, or appear to be the same volume, let's say. Okay? Does anybody have one of these killer subwoofer things? Like, you've got a really nice stereo at home. Anybody? I've got a kind of crappy
I've got a
stereo.
really big guitar amp.
I actually have a really good guitar amp too. But so it's interesting. If I wanted to get this, let's say, 24-inch subwoofer. Let's say it's a real serious subwoofer. What else do I need? I can't just have the speaker. What else do I need?
Amp.
How much power?
Depends on the speakers.
I'm serious. How much power do I need to drive a 24-inch cone forward and backward like
100
this?
watts.
100 watts?
That's what I'm saying. That's what I'm going with.
What can you purchase on the street nowadays?
600 watts.
That will edit out.
What did he say?
You can get, what, 3,500 watts? You ever seen these things? Why do you need 3,500 watts? And
you're
yeah,
beating
some
down
people
the
say
block.
you don't need it, but why could you need 3,500 watts?
Beating down
A
your
lot of
block.
speakers.
Because of that subwoofer. Now look at why. Okay, do you need 3,500 watts to drive a tweeter? Probably not. All right, this is why. It's because the equal loudness contour. If you look right here, here's the sound pressure, 90 dB, something like that, and you can see the frequency right here. Basically, this is the amount of power that it's going to take to create an equal loudness for all of these frequencies. What does this say? We're not very sensitive to around 20 hertz. Everybody look at this chart, right? So it's going to take a whole heck of a lot of power for us to perceive that 20 hertz. What happens as that pitch increases? It takes less and less power. To a point that about right here, notice the ouch. Okay, 4 kilohertz. You are hypersensitive to 4 kilohertz. So if somebody plays this, it doesn't take a whole lot of power till it gets in your ear. You ever hear those frequencies that just hurt?
Yeah.
You're like, oh! It's because that's where it peaks right here. Okay, it's probably at this 4 kilohertz or maybe somewhere around here. It doesn't take a whole lot of power. You're really
Yes,
sensitive
exactly.
to those frequencies. Does that make sense?
Yeah.
And then it fades off right here. You can see that we just stopped hearing at about 20 kilohertz.
Shaw says that's the mom voice right there at the ouch.
The ouch?
Yeah.
The mom voice?
So true, though.
Yeah.
I guess because at that point, the reason why it's so uncomfortable is because it's almost like radiation at that point. So like, well, because you know the wavelengths are so tiny and so fast, that it's like
It's just your ear maybe resonates with that, or you're really sensitive to that. Okay, so a thing about decibels. What do we know about decibels? It's how we measure what?
Sound. Intensity.
Volume. Okay, yeah, I knew what you meant. Intensity. It could be like a great song. Okay, it's abbreviated this, but a decibel is 1/10 of a bell. That's why it's the lowercase d. This is the perceived loudness, which increases linearly as power increases exponentially. Okay, so there's this exponential kind of thing that's going on. So something sounds twice as loud. Don't go through that. In gaming, basically, you just have to understand that it's going to take more and more power to get that increased volume. I'll just leave it at that. Okay? We talked about this. This is human perception. You can see that's the interaural time difference is what that's called. Okay? Now, tying into gaming, how is it that computers deal with sound?
Ones and zeros.
I want you to think about what we're doing. We have an analog discussion that's going on right now, but I have a microphone that's in front of me that replicates what's going on. Now, what do computers store? A whole bunch of ones and zeros. So we have to somehow take this analog thing that's going on and convert it into ones and zeros. What's the process?
Changes the frequencies.
There's different encoding.
Electronic signals.
How about this? How do we hear sounds from a computer? Okay, so watch what the speaker's doing. A speaker is usually a cone, yeah? And what does that speaker do? It moves in and out. And so what is it doing?
vibrating.
It's vibrating, it's pushing, and it's creating these compressed sections of air and then uncompressed sections of air, and it's spitting those out into the environment. How does a microphone work?
It's much the same, except it's vibrating in resonance with other sounds.
Right.
Recording that down.
So this goes back to that disgusting example that we talked about with me resonating your ears right now, right? The same thing is going on with this little tiny cone that's here. So is a microphone the same thing as a speaker? Believe it or not, it is. And if you are truly desperate, you can use your headphones as a set of speakers. It's not going to sound very good because that's not what they're designed for, but I've actually plugged it in, and if you yell and you take it, whoa, like that into the headphones, it'll actually record it. I kid you not, because it is a very poor microphone. So they're basically the same kind of thing. Now, if this mic is moving in and out, right, at however fast we're talking, how does it then get converted into ones and zeros?
In, out, like 1 and 0 and zeros.
If you think of it this way, you know that there's a maximum distance that this cone can move forward and backwards, right? So let's assume that at rest, there's no sound that it's picking up on. That cone is at 0. You with me? If it's all the way this direction, let's say that's 1 and this is -1. It doesn't really matter which one is positive and which one is negative. Okay? So what can we then do with that information? All I have to do is sample where the cone is at a particular time and then write that out to the hard drive. How do I undo that operation? If I wanted to play something back?
Tell the cone where it should be.
You think about it. That's what an audio file is basically where that cone needs to be at any given point. So we just need to move this cone kind of back and forth, and then we have everything. Okay? So how fast do computers listen to this cone? The CD is 44K, right? 44.1. You probably heard that term a couple of times. 44,000 times per second. I want you to appreciate what it is that your computer's doing when it plays back some kind of audio for you. 44,000 times a second is what it's using to record your band or something like that. 22K. Does that sound pretty good? Yeah, not too bad. What about 8K?
Yeah.
Has anybody heard a really low sampled audio clip before? I still remember the first time, and this is probably predates many of you, the first time that I ever heard a computer do something that was not a beep. There used to be, you know what magic mushroom, no, I shouldn't say that. Magic mushroom air fresheners are? You ever heard this? It used to be these things that you could like plug in, like Blade plugins and all this other kind of stuff. They had this little catchy tune. Like, there's a mushroom in the bathroom and all this kind of stuff. Somebody, for whatever reason, recorded that commercial and then sent that file out, and you could play it over the PC speaker that was about this big in the front. And I thought, oh my gosh, this computer is now singing the Mellow Mushroom or the Magic Mushroom song. And I couldn't believe it. I remember the first time I heard an MP3. You remember the first MP3 you ever heard?
Not really.
Probably not. Mine was an ABBA song.
Yeah.
I don't know why I'm having all of these horrible audio experiences, but it was Take a Chance on Me. And I remember thinking, oh my gosh, this sounds so good. And you know, the next thing's going to come out. What's the next thing going to be? I don't know. It sounds like you're actually at the concert or something. Who knows? 3D, you know, it's not going to be ABBA though, right? So, and I've got another story about ABBA too. That was the touring band before I was touring with Duran Duran, and the ABBA band.
That's awesome.
But ABBA, there was an ABBA knockoff band that was there every step before, so they would be tearing down when we'd be setting everything up. Anyway, computers have to approximate what they heard and assign it a number. We already talked about that. Realize when the approximation goes on, we have to represent where this cone is with a certain number of bits. Now let's do the math. If I have 1 bit, how many different variations can I get? 2, right? It's either a 0 or 1. 2 bits, what can I get?
4.
0, 0, 0, 1, 0, 1, 0, 1, 1, all that kind of stuff. I get 4. So if I have 4 bits, that means I have 16 levels of approximation to where the cone is supposed to be. Does everybody follow me? Because you know these are going to be on the exam, right? So just try to pay attention. So I have 16 different ways that I can represent where this cone is supposed to be. Is that good?
No.
That's awful, okay? If I were to use a 4-bit sample, right, what is that going to sound like when I play it back?
NES.
It's actually going to have a whole lot of hiss. It's going to be this shh. You can hear all this kind of stuff in there. Why? Because it's having to approximate. It wants to be, let's say, halfway between those two positions, but it has to either go forward or backwards. It can't be the two. So what do we want to do? We want to take the number of bits per sample up as high as we want, right? 16 bits. How many combinations can I get out of 16 bits?
2 to the 16.
Don't say 2 to the 16. Technically, you're correct. What number is that, 2 to the 16?
About
2 million.
Oh, well, okay. Never mind. Okay, here's what we're going to try to do. We'll visualize this. You can see we've got an amplitude. Let's assume that this red thing is an analog signal that we're trying to capture. Okay, we have amplitude, which is the height, right? And we also have the frequency, which is the distance between these two peaks. Okay, so if we have a low sampling rate, watch what's going to happen. Here is the red is the original, and we sample at these particular times, which are represented by the vertical lines. So what does our final recording look like?
Yeah.
You said it's pretty close. No. It sort of has that waveform. Again, I go back to the original, and you can see here it missed this peak here in the middle altogether. Right? And again, the result sound is going to be this kind of muted. It's not going to have a very crisp sound, and there's going to be a lot of hiss to it. Okay? So what do we do if we take it up to a high sampling rate? We get something that looks like this, okay? Now, what about 2 bits per sample? Now we can visualize the bits per sample with horizontal lines here. If we do something like this is 2 bits per sample just to show you what this looks like, you're going to see that we have to make decisions. In fact, I'll take it back to this. Notice this sample right here. Okay, this is going to be hard to hear on the audio. What's the problem with this sample and these other kinds of things? Why is that such a problem?
It's gonna EQ, the EQs are sound weird.
You're going to have to force it to either go up or to go down. We only have 4 levels that we can approximate to. Does everybody see that? So in these sections right here where it's between 2, I either have to push it up or I have to push it down. And again, this is going to cause all sorts of problems. We get this kind of stair-stepping thing called a quantization error, right? Because we're trying to quantify these things to be an absolute value, and that's what we get. So how can we solve this? We can add an extra bit in this case. So we have 3 bits per sample, and you can see that it much more closely approximates this, this sound that we're trying to capture. So do you get it? So can you, with confidence, explain bits per sample, why it's necessary? Maybe a little bit later after you study at 3 o'clock in the morning. Okay. We also have a signal-to-noise ratio. I'm not going to talk about this too much, but basically this is going to represent the quantization error. Yeah, well, let's go ahead and talk about it. So if we have 8 bits, right, we have 128 discrete values in just the upper half. Now let's do the math here, right? 8 bits gives us 256 possibilities, yes? Right? So that's 256 levels that I can approximate to. It's 128 in just the upper half alone. Right? So we're doing pretty good. The sample is rounded up or down. We know that. So the signal-to-noise ratio is 256 to 1. Why? I know what you're saying, because it's 8 bits, and that's 2 to the 8 is 256. Why is the signal-to-noise ratio, what does that even really mean? Signal-to-noise.
For every 256 signals,
That's saying in the worst case situation, how far are you going to have to move this thing off of where it really needs to be? What's the worst case situation that we've already seen? If I have a whole bunch of different levels that I can approximate to, what's the worst case situation? It's in the middle, right? So what we're saying is that the distance between the worst case situation is 1/256th of a movement. Does everybody get that? I don't want you to draw out 256 lines and do all this kind of stuff, but I do want you to understand, if these things are this far apart, 128 just in the upper part, what's the most that I would have to move that to get it to fall onto one of these lines? It would be 1/256th of that. Does that make sense? The signal-to-noise ratio. Okay. In general, if you have to sample stuff, does anybody really get into audio and try to record things? Like, oh, I'm going to make my own sound effects? Don't. But if you have to, you have to deal with something called the Nyquist theorem. The Nyquist theorem states that you have to double basically the highest frequency that you're going to sample, you have to double that in your samples per second. Okay, so if we're trying to record something at 10,000 hertz, what's the ideal situation I record? 20,000 or 24,000 or something like that. I have to make sure, and that's going to allow me to capture that. Okay. What about recording? Here's some interesting things. You guys probably don't do this. Do you listen to NPR, classical music?
Yeah.
A couple of you, right? What do you know about listening to classical music? You turn on NPR, and a lot of times, you're scanning through, you go, 100.5, and you go all these different kind of things, 105.3, and then you hit NPR, and you hear nothing. But wait, there is music there.
It's the really low stuff.
And you turn it up, and you turn it up, and then you hear, ooh, and it's like, hey, I hear some symphony stuff there, and then what happens?
It gets really loud.
And then all of a sudden it blows out your ears, and bam, 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 and then it'll get back to this little song. And it keeps doing that, and it makes me so upset because I can't listen to NPR because they have these explosive sections, and it drops down to nothing. Why do we have to take that into consideration when we're talking about all of this mess?
We don't want to deafen people who
Well, you don't want them to go deaf. That is true.
That's true. But
How is rock different than Mozart?
it's a
Sort of range of sounds and frequencies that are in it.
Think about what rock does. And we'll just use rock as an example. If I turn on a rock station, what am I going to hear?
loud music.
Loud music.
Guitars and drums and everything.
Well, always loud music. For the most part, rock is just like all on, all the time, and it's just noise, right? Okay. How is that work different than Mozart? A section, yeah, it's all of this kind of stuff where it gets loud and then it drops down and all these kinds of things. Why is that so important when we're talking about recording? Do we have to take anything in consideration?
Yes.
How big is the wave in an NPR recording when it's really quiet? It's really small. You've got these little things, just like this, right? Why is that so problematic?
Because when you replicate the sound on your speakers, it moves, but only
Here's the problem. We have to approximate up or down, yes? Right? We have these levels that we have to approximate to. What if my music is just going like this and it's real small? What am I going to hear? Yes. I'm either going to hear nothing because it rounded everything to 0. That would suck. Or I'm going to hear a lot of hiss because it's having to approximate up where it doesn't really want to do that. You ever notice when you turn it up you hear a lot of hiss? It's because of that. Okay? So what can I do if I'm recording rock?
Record each instrument separately.
Well, I could do some tracks. I could lay down some tracks, yeah. That's a good point.
But the sensitivity for those frequencies are...
You could set sensitivities. Basically, you could customize it to say, we don't need a lot of levels here of approximation because we know that it's always up at these extreme kind of values, right? So we can do that. What about voice? How does voice differ?
You want your voice to be really low and the music covered.
Think about rock. What instruments do you have in rock? Guitars, yeah. Keep going. Drums. What's unique about drums? Yeah, they're loud.
Different pitches.
You have what makes up a drum set?
Cymbals.
Cymbals.
Snare drum.
How high are cymbals? Right, really high. What else is on there? Bass. Right. So you think about the range of frequencies that you have in rock versus a human voice.
It's all dependent on the person.
You don't have this beautiful range, right? You don't have a huge range when it comes to voice and dialogue, so you can cut back there as well. Okay? How do you capture sounds? Microphone. Google. Go out there and just steal stuff. Yeah. Okay. Speaking of which, it's not stealing if you do that, of course, in this class, and you're not selling it. Did you see the link that I sent you, Open Game Mart? Did anybody check that out?
Yeah.
A lot of cool stuff there. I would recommend that you do that. There's free music, gaming kind of music that you could use and everything else. But yeah, typically what we do is we use a microphone, we use line in something like that, and we just record things with Audacity or whatnot. Okay? Here's the pipeline. No, we'll skip the pipeline. That's from the book. Let's get into, and then we get into compressed audio. What are the popular codecs? Actually, take a step back. What is a codec? Compression, decompression. It's a way to compress these files down, okay? We have two different kinds. We have lossless and we have lossy. And this is true with video and image filters and stuff like that, too. What is lossless?
Best quality.
You can replicate the exact, if you compress it down, you get back exactly what you compressed, right? How's that different than lossy?
You lose stuff, but it's a smaller file.
You lose stuff. You can't replicate exactly what it is that you're trying to do. Now, what do you know about MP3s? They sound awesome, don't they? Are they lossy or lossless?
Lossy.
What about a WAV file?
Lossy.
I heard a mixture there. WAV file is lossless. Okay? Now, they can compress these things, but also, it's interesting. How do MP3s work?
You think I did this.
Magic. Voodoo, yes.
Magnets.
Lots of voodoo and stuff like that. Believe it or not, they did a lot of psychoacoustics here. The reason that MP3s sound so good and are as small as they are is because they're playing off of you being human and that you're more sensitive to some frequencies than other frequencies. Have we seen that before? The equal loudness contour, right? So they try to emphasize those things. They discard sounds that we don't normally hear anyway. And so they cheat. They strip out frequencies. And that's how MP3s work. So you should dump a whole bunch of MP3s in your game, right?
Yes.
What's the problem with that?
Isn't there like a copyright?
Copyright issue.
Yeah.
Yep.
MP3 is not a open
MP3
source.
is not open source, as is a bunch of stuff. Or as are?
That's all.
As are a bunch of things.
Who cares? It doesn't matter. This is not English,
plural.
right? It's plural, so whatever. Okay. So what are you supposed to use? OGG? Great alternative there. In fact, you're seeing a lot of things that are moving into the OGG realm. It does a great job. Okay. Other things that you're going to hear about. This is for defining the volume of sound. It's called ADSR: attack, decay, sustain, and release. So if you hear a sound like a piano, somebody goes, ding, how would you describe that in terms of ADSR?
Okay.
What would this look like?
First, a high sound, and then
Without percussion.
Okay, what does the attack look like? Let's do it in phase.
Very sharp.
It's straight up. You think about it. A piano is a percussive instrument. It drops that hammer down, it hits the strings, and it resonates immediately, yes? So our attack is almost straight up. What about the decay? Yeah, it kind of drops off fast, and then it's real gradual. And then what about sustain? That's the section there, right? And then release, when they let off, it drops off pretty fast. Right? So you can describe almost all sounds this way. Okay? Yeah, skip that. Okay, now this is important. Couple of things, and this will pay off a little bit later. If you're really good at this, you can pretty much have a job in doing audio. You ever heard of Fmod? Okay, think of your favorite game that you've played. Borderlands, My Little Pony. No, I'm just kidding. I'm just kidding. Anything that's got a lot of complex audio. How much audio is in there? What kind of audio is in there? Okay, a lot of dialogue, a lot of ambient sounds. You know, you always, if you're in a desert, by the way, what do you always hear? No, but there's something. If you can hear tumbleweeds, that's pretty cool. You always hear that bird that goes, and they say that's the most cliche thing ever. So if you ever do a desert scene, don't do that, okay? But anyway, you can hear potentially the birds, potentially the tumbleweeds, potentially gunshots going off in the background. You can hear a whole bunch of people talking all at the same time. The question is, how are you going to do that logically in your game? I want you to think about this. If you're putting together one of these massive AAA title kinds of things, how complex is audio? Very complex. Extremely complex. Okay, it gets to be really nasty really fast. So you start looking into SDKs that are dedicated to sound designers and things like that. Fmod is one of these. You're going to see Fmod, and another one's called WWise. You ever heard of this one? Those are like the two major ones that almost all games that you've ever played have probably used, okay, unless it's a really early kind of game. So the reason these things are so cool is because you'll have a sound designer. What does a sound designer do? They may make the sounds, but a lot of times they just have libraries that they've collected over the years, or somebody's given them to them. What does a sound designer do? They think about just the sound aspects of the game. So if you walk into this room, right, let's say that we have a game that's going on in this room. What kind of sound things might we have? Me talking fine. What else? All the stuff that you're hearing right now. So how are we going to organize this? How are we going to put reverb? Is there any reverb in this room? Absolutely. You don't hear it right now. If you were to listen to the recording, you would hear it bouncing off the walls and all this other kind of stuff. You just don't notice it because you're here in the room. But there's, can you hear it now? All that stuff, right? I can simulate it. I can just say, you know what? This is the reverb level of this room. I could put it in a cave. What do you know about caves? They echo for a really long time. So you start to look into SDKs that support all of these environmental effects like reverb and what's the difference between reverb and echo?
Echo comes back.
Echo is a repeating, right? And then you get occlusion. You think if I stand here and I talk, they can hear me in that other room?
Not as well.
Oh, and that's not what I asked.
They can. Yes.
Can they hear me?
Yes.
Yes, they can. What do I sound like? That's what they're hearing. Unless they put their ear to the wall. But yeah, for the most part. So you have things like occlusion. If there's a wall, you don't get a lot of those high frequencies. Obstruction, no direct path to the listener. You think about this. Assuming that the walls are totally soundproof and everything else, how is it somebody can hear me way down there and what do I sound like? Think about all of these nasty situations, right? What about fading out? And then you've got this other thing that fades in. It gets really complex really fast. And so you start to look into things that support these different environmental effects. Okay? One of the last things we're going to talk about. How are we doing on time? 5:20? Why'd you say oh? You were so involved. Oh my gosh. I thought it was just 5 minutes. Or like, oh crap, we've got another 25 minutes. What is MIDI? MIDI is one of my favorite technologies, but it's not really as popular as it could be.
Oh.
Yeah. Does anybody know?
Yes.
It's
Yes. The musical instrument digital interface. What he said. Yeah, but how does it work? How is it different than an OGG, an MP3, and all of these other kinds of things? It's a simulation. Okay, so you can imagine, in fact, I've got one of these and I'll threaten to bring it in one day. But it's a MIDI keyboard, right? So as I press this information down, right, I'm pressing down keys and I'm playing whatever it is, I send the signals out to a computer that records not the sound. What is it recording? Key presses. How hard you press it, the velocity of the key, all of these kinds of things, it's recording it into this exceptionally small file. Okay, so the question is then, how do we undo that operation? How do I hear a MIDI file? I mean, you think about it. If I can open this up, I could open this as a text file, and I could say, you know what, I see all of these kinds of things. Okay, fine, I'm reading through it, and then I know that I need to play a brass instrument at this particular time this loud. It doesn't matter what the instrument is. It can be a guitar. But what do?
Get a library of sounds.
You have to have a library of sounds. You have to have a graphics card that has a whole bunch of pre-recorded instruments on it. Sound card. Did I say graphics card? I'm sorry, I haven't had enough. Sound card. I've been teaching graphics too much, you can tell. But anyway, that's what's working, right? So imagine all these ones and zeros that represent on and off kind of signals that are reinterpreted through this sound card. Now, what's a potential problem with that? The sound card's not very good. You may have a $3,000 sound card, and you may have a $50 sound card. Are they going to sound the same? No. Okay. So you can imagine that when, what's that? Yeah. Yeah. Will they make a $3,000 sound card? It's not for your computer, though. It's for doing professional kinds of things. And if you want to see one, I'll bring mine in. No, I didn't pay $3,000. I eBayed it and got it at a significant discount. Anyway, so these became really popular in the 80s. They use MIDI for just about everything that they can trigger on and off. Like you can do virtual drums. You can actually use MIDI to control doors and all sorts of weird stuff. The virtual drums, yes. If you've heard any 80s music, you've heard virtual drums.
The same drum set in every song.
And how potentially bad they are. Yes.
Do you use Guitar Pro?
Do I use Guitar Pro for what?
It's the same thing. That's just,
Yeah, it's like you can download
That's just
if you just have the program itself, it's all MIDI. But if you get like the sound banks, then it actually sounds pretty cool. So.
Have you played Rocksmith? Has anybody played that game?
No.
Don't. I asked for that for my birthday. I said, sweetheart, please get me this game. I want to see what kind of cool stuff they have. And it's not. And here's the problem. And we'll edit this part out. If you want to learn to play guitar, come see me. I'm not the world's best guitarist, but I'm not that. Okay? Go to Google and say, I want to learn how to play the guitar, and you can learn anything that you want to learn off of Google. That's the truth. If you want to learn how to replace your radiator in your car, go to Google, and it's going to take you to YouTube. Here's a video, right? You can find it just about everywhere. Anyway, getting back to this, limitations have 128 possible instruments. Some of these are kind of weird, like helicopters and birds, and I don't know why they originally. Police sirens, yeah, gunshots, walking, and I don't know why it was there. But realize that that is an option for you. Okay. We generally talked about all of that. There's an intermediate step here called the sequencer. If you wanted to record, we talked about putting tracks down. So you can say, okay, now I'm going to play the drums, and you can actually play drums on a keyboard and have this thing that records it. Typically, that is a PC. Okay? And here's what I own. Right? You wanted to see what it looks like? This thing right here is a fancy sound card. And it has thousands and thousands of sounds that used to be professional and now are probably not as professional as what's there. But it has just about everything that you could possibly want. It doesn't matter. It could be singing, it could be choirs, it could be orchestras, it could be brass instruments, drums. It's got everything. But anyway, this is the last stop right here. This is what actually produces the sound. Okay? Oh, wait. No. Speakers produce the sound. Yes. I should say yes. Okay? So there's your configuration. Does that make sense? Questions? It almost sounds like a test question, doesn't it? Yeah. What's the difference between MIDI and wave file, and how do they work, and these kinds of things? Was that? Yeah, but I would ask you, how does it work? So if you had to explain it to someone else, what would you say? Are the kinds of questions? Just to say, if you sit down in a job interview and somebody asks you these kinds of questions, could you answer them?
I'm a programmer.
I'm a programmer. I don't need that. Yeah.
That's not my work. I can hire you.
Let's
That's
see.
above my pay grade.
Yeah, okay, I'm sorry. There's one last kind of fun thing.
Oh.
If you've ever heard of FM synthesis, if you want to go really old school and get these kind of 8-bit game kinds of sounds, there are four primary things, but I'm going to show you a couple different ones. The Commodore 64, I don't know if you've ever heard of this instrument. That was my first computer, and I loved that thing, but it had the unique ability to play 3 sounds simultaneously and also play static. It had a static chip. It was like this white noise. That it was, because if you need an explosion, what are you going to do? You're not going to play. That sounded like an explosion. So that was your explosion chip, if you wanted to think of it. But anyway, I'll let you hear what these things sound like. And if you listen closely, a sine wave, everybody's seen this for a long time, is this very smooth wave. And I want you to hear how smooth this sound really is. Okay? Notice there's not a lot of what's the best way to sounds like this, real high overtones and all this other kind of stuff. It's just one pure kind of sound. Now, what do you suppose a square wave looks like? Okay? It goes almost straight up, flat, and then it drops down and flat, and then it goes back up and flat, and so on. Listen to this one. Whoa. Let's try it. Okay? Here's sine wave. Now, this was what a lot of synthesizers used. Like, you ever heard the Van Halen song Jump? That was a square wave instrument, all that kind of stuff. Here's a saw wave, and this is a what? You have to be careful. There's 2 different versions, saw and triangle. And I know it's a slightly different version. What's the difference between a saw and a triangle? You think about it, a saw is like a sawtooth. It goes straight up and then down and straight up and then down, versus a triangle, which is kind of like this. But you can see these fundamental kinds of things, and I can play noise if you want to hear noise. Okay? But you can see these fundamental kinds of things. You can start to mix them. Okay? FM synthesis says that you take one and you feed it in to modulate another one. So you have one that's affecting the sign of another one, and you can get all sorts of interesting kinds of things. And I know what you're saying is, well, what? There is a 440 sine wave being controlled with another one at 2 hertz. Can you hear it? Think about what's going on. Right? You can hear the 440. That's that sound. And then you've got the 2 hertz, which is going like that. It's controlling the volume. Now listen to this. Here's a 440 sine wave controlled at 880 hertz. That sounds familiar. Okay? 440 sine wave controlled at 3 kilohertz. What is this going to sound like? It's almost like you get the same thing back, right? So you can start to mix and match these things, and it was theoretically possible to get any sound in the world. In fact, why does a clarinet sound different than a trumpet? They can play the same tones.
It's the medium and what the instruments, the resonation.
But why does it sound different to me?
You're vibrating brass.
Because isn't there like multiple resonating frequencies?
There's frequencies that are above it. Even my voice right now, if I go like that, there's a whole bunch of frequencies that are up above just the bass kind of thing. So it's interesting in that way. We had already talked about interactive music, so this will be the last thing. Themes in Fmod right here. Here's an example of what Fmod looks like. You can see it's a graphical application. So I can transition between these themes, and what a theme is a different point in time in the game. So you might have something here on the left like this is the adventure mode. Like they're going out there and they're exploring and they're riding the horse through the field and all that kind of stuff. And then you transition to where all of a sudden it's not so pretty. It's not so green, let's say, and it gets to be the scary evil section. And then this might be a boss fight, right? And then that could transition here into some kind of cathartic release where everything you win the game kind of stuff. So we can set things up graphically, and this is what the sound designer would do, and then we take that as programmers, we take this big bundle of stuff, and we're able to access all of the variables that the person designed here down at the bottom. So I can trigger things and I can do them all programmatically. All right, I think that's it. There are a couple more slides after this, but I'm not going to talk about it. Any questions about audio? You can see there's a lot to it. And again, I tell you that you need to specialize in something, like you're going to go into mobile or ed or series or something. Another thing that you could do is to go in and become WY's master or an FMOD master or something like that, and just say, this is what I want to do. And you would probably have a job. But you have to be good. That's always the case. All right, so what's due on Monday? Something specific.
Video.
A video. How long is the video supposed to be?
20 seconds.
These are loose guidelines, right? 20 seconds to 2 minutes. And is anybody going to do a 2-minute video? It's a possibility, but you better have some stuff to show. And you don't have to talk, right? You can just record the video. I'm assuming that you'll be up here. You have a YouTube link. You have something. It doesn't really matter. And then you can talk over about, okay, you can see we had the basic things. Here's our game. And then we'll do some comments. Yes? Do you submit the file in D2L? How about this? If you send me the link to your video just like we did last time, I'll try to have a collection of those things so you can just walk up, you can click it, you can say, here's my game, here's the mechanics, here's the thing we struggle with, and then you can sit down.
Here's a button.
Yes?
Do you have a specific software that you would suggest that we use for the video? Perhaps.
Okay, so the question was, what video capture software should we use? And Fraps is pretty much the most popular one. You could look into other things like Camtasia. There's free versions of Camtasia that can record for longer periods of time. But for the most part, your video is going to be pretty short, right? I would imagine 30 seconds. I think there's a limit in Fraps of 30 seconds, something like that. So keep that in mind. What else? Other questions? Yes?
What kind of amp do you play?
What kind of amp do I play? I'll take a picture of it. In fact, I think I've got it on my phone. I always take it with me.
It's a tube amp, right?
It is a tube amp, yeah.
Thank God.
Of course, yeah. I had an option. But we can talk about that offline. Any other questions that are not related to my amp?
Chainsaw.
Chainsaw. My chainsaw is doing well. I have an awesome chainsaw. Yes. It's a Stihl, if you've ever heard of Stihl products. It's quite good. I will not bring it to school. Anything else? All right, so you guys have a good weekend. Work, get a minimal implementation, and I look forward to seeing you on Monday.
I'll show you the syntax that I showed you.